Yankees are the Patriots. I'm happy.
So,
I won't argue with that, but
it was a quick way to do everything. It's bad that the spacecraft didn't launch well, but it is good that there are they both are safe, the crew. So, what do you remember? I'm starting from the freezing question. Yes. What do you remember from previous class, from previous time?
we had a staircase.
Staircase. Who was walking on the staircase?
Oh, was that?
Okay. What this guy was doing?
One to different energy levels.
Yes, and important thing that this guy was looking back behind. So how like walking onto stairs and counting how many flights are behind. Right? So we were expressing number of states as function of energy where we are, where this guy is, right? Make sense? You remember it? And then we were taking derivative of number of states and getting density of states. So, so the plan is to establish a person walking on the stairs, look back, count number of states as function of energy, and make derivative. And then you will get density of states. Why are we interested in density of states? It looks like you're not interested. Well, okay, if anyone in this world is interested in density of states, why he or she would be?
Get a good grade in this class.
Come on.
Sorry.
I'm interested in your grades maybe more than you are. I know. No, in the big life, if any of you will go to like research and development in company or academia, who may need density of states? What are their benefits? Because otherwise there is no reason to use them.
Will it help you predict what energy level will take you to a different excited state?
Not bad, but it is rather specific. Is there anything from the bird's view? Bird's view, not that as stupid as a bird, but from very far above, looking on the big picture. Like, what are we studying here in this chapter?
Electron in a box?
Yes, and in your homework in your lab, you were doing the multidimensional box, 2, 3. And you already have an idea how the density of states for them look like, right? So were there any trends? Were the density of states all the same, or there were some specific features? Here I'm formulating the question that okay, in next sentence. I know the answer, and I hope very much that you know the answer. If I will show you a density of state, one of the 4 types that you were exploring in your homework, 0D, 1D, 2D, and 3-dimensional bulk. If I do not label it, which one was it? If I show one of the 4, would you be able to recognize which was it?
Mm-hmm.
You did answer the question. Now, let me ask again. So you need just a little verbal effort. What is the benefit of knowing density of state? Who needs density of state? You already did it.
knowing the shape of the box?
Yes, by looking on density of states, you can reconstruct shape of the box. In a narrow sense, in more general sense, any chemical, physical object, quantum object, has its own density of states. So density of states is a signature of structural properties of an object. By looking on density of states, you can reconstruct which object is in front of you. And since we are working with a microscopic world, like you cannot isolate one molecule and look on it, right? But there are instruments that would measure density of states, and by looking on them, you can reconstruct what the molecule was. If density of states is not possible and not reliable, there are several other characterization tools that would allow this reconstruction of what we are working with. Make sense? So, any alternative opinions? What are other benefits of density of states? Now Ben is allowed to speak.
Well, we can look at like where the electron would go when it's excited.
Okay. Yep, makes sense. So it is correlates with original suggestion of ours, right? Which excited states at certain energy.
Yes. So in addition to reconstructing original model, if you do not know what the model was, it also gives some properties like would it be able to absorb light or conduct electricity? There, one can make the course which you have titled "Density of States" for half a year. For example, metal semiconductors insulators. By looking on density of states of an object, you can decide whether it is metal, semiconductor, or insulator. So metal has density of states starting right from zero. Insulators started very far from zero, and semiconductors are between. We'll return to it later. So on today and on Monday we finish this chapter and we'll start a discussion of oscillations next week. And another thing I want to give you heads up, in about 2-3 weeks we will have another chance for presentations. So we'll go into details, just giving you heads up, and we'll be doing the practice of democracy, so we will select what we want to present. Within a certain range, not like life on Mars this time. Also, by next Wednesday, you may try to entertain yourself by one of the pen and paper homeworks. And I should have printed it, but instead I probably will just email it. And it is in the third slide of slide that I distributed. And here is where we are. So we do have many tools, and right now we apply them only to 2 objects, but as time goes by, we will apply them to different models, more and more applicable to real life. Right? We for box, we done time-dependent Schrödinger equation, time-dimensional equation, density metrics for time dependence, and now we are practicing density of states for the reasons that you have already verbalized and yourself, and we already discussed, right? Recognition and prediction of optical and electronic properties. So I think you already enjoyed this. You were able to generate this video. So as long as the box is growing, density of states for this box changing shape from discrete to 1 over square root of 2 Markov singularities to the steps, and then it forms square root of energy, right? As it gets more bulky. Yes. So the question that we were discussing was about like there are no labels. Well, unfortunately, they are ordered, so you can guess which dimensions are there. But let's try. What's the first one? How many dimensions? Zero. How many dimensions? How many dimensions? How many dimensions? Perfect. Okay. Now we have a perfect contact and involvement of all class in the discussion. So this one drops 1 over square root of energy, this one grows 1 over square root of energy, this one is flat in between. And see, the offset of the first energy, ground state energy from zero is the signature of quantum confinement. The more confined the system, the further this offset is. So for 0 dimension, which is confined in all 3 directions, it is confined at most. And then if you go to 1 dimension, it is less confined, and almost and no confined. Okay? So when you squeeze, the energy increases. Good. So if you see steps, you go, oh, okay, it is a thin film. If you see this 1 over square root of E, you go, oh, sure, we had it in the class, I know it is 1 Hopf singularity. It's typical for carbon nanotubes. If you tell it in the presence of someone who studies nanotube, you will impress him or her. If you will be taken CHEM2, your instructor will be in primary research area of carbon nanotubes, so you'll have a chance to. Okay, this is just summary, and most important is this person. So a person who walks on the energy axis and looks back. So it will be our helper in today's meeting. Why? Can you guess what are we going to do today? Any ideas?
Density of states.
Yes, of what? Of which, last class, we derived density of states for one-dimensional nanowire or whatever. But in homeworks, you did both nanowire, thin film, and bulk. What is your guess? What are we going to do today? Yes, to derive analytical equation for the shape of density of states. Okay, and the protocol, like in the last class we got this 1 over square root of E. Today we are going to get these steps, or at least one step. And we are going to use this walking along energy axis, looking back, how many states, what is the number of states behind certain energy. And then upon selecting this number of states, we will be taking derivative of numbers of states in respect to energy. Okay? There is one practical skill that we all should inherit from our middle school or high school, and I want to count you in this little background knowledge. What is the area of a circle? Excellent. I knew that I can count. Let's go more crazy. What is the volume of a sphere?
4/3 pi r cubed.
4/3. 4/3 pi r, which cube? Cube. Yep. Thank you much. So now you have all pieces of information to derive this stepwise density of states and slowly growing density of states for three-dimensional. One of the ideas would be for me just to give you blank pieces of paper to like derive. No? Okay, I'll do it for you. Well, but if you would decide by some reason to do so, what would you do? Let's just make a plan. What is missing? We have general direction. Count number of states behind us, behind certain energy, and then take derivative. So how do you count number of states behind certain energy? So for, yes?
Hamiltonian?
This is general answer to all questions. But practically, like if someone gives you energy, you already know the Hamiltonian, you know which system you're working with, and the question is how many quantum states have energy of this energy or less?
The eigenvalue?
How many eigenvalues are behind this certain energy?
Sum of the delta function times E minus EM.
Yes, but how far the summation should go? In the sum that you were mentioning, we were making summation from 1 to infinity. In your homework, infinity was set up to 30, but generally it is more.
Times the E0 n squared.
E0 n squared. Yes, this is absolutely correct for one-dimensional case. Remember, look what Alex told. Like if we are in one-dimensional case, the energy is E0 times n squared, and then n is a square root of E divided by E naught. That's it, right? So if we are in one-dimensional case, we already have the this equation. N equals square root of E over E naught. But this is for one-dimensional case. Now we need similar style of equation for two-dimensional case and three-dimensional case.
You just add whatever dimension you're adding to. So if you have like x and y, you take E naught x times nx squared plus E naught y times ny squared.
Let's try. So E x E naught x plus E y E naught. Something like this. Interesting. We can try. We can try. Yes. We will do it. I never thought in this way, but it's a good direction of thought. So okay, here. So square root of energies, of summation of energies along x and y. This was not a bad idea. But the specifics of density of states, that it should be universal. It shouldn't be, it should be only one parameter. It should depend on energy independent how many dimensions is in the system. So we should go back to only one energy as a parameter. So when we are speaking about density of states, we cannot insert their like density of states as function of two energies, three energies. We need only one, right? And we need a procedure that will unify energies for one dimension and another one. So I am inviting you to an to visit an abstract space. Typically, we are in space of Cartesian positions. A while ago, we were in momentum space, and now we are entering the space of quantum numbers. So, when we were speaking about one dimension, this space was boring. It was just a set of quantum number n equals 1, 2, 3. So very simple. But right now, if we are speaking about 2 dimensions, there will be 2 quantum numbers, right? Quantization in x, quantization in y. Make sense? Or should I track back and come recall where it comes from? No? Everyone is fine. So energy is summation. If our electron can move in 2 directions, wave functions are products. Wave functions, overall wave function is product of motion along x and motion along y, and energy is summation of eigenstates associated with motion along x and along y. Right? So it's, we can call it Alex equation, or Hart equation. E m x and y equals E naught x and x squared plus E naught y and y squared. Right? But our parameters are this nx and ny. Suppose that our scaling factor E naught x and E naught y is the same, just for simplicity, so that it is square plate, like in a sushi restaurant. Sometimes they have triangles, sometimes they have square plate, or square pizza. Then the energy of an x and y will be just E naught times n x squared plus n y squared, right? No cheating. You're so surprised because you were expecting some traps and something complicated. No, it will be simple. So if it would be not n and x and y, but just x and y, what is x squared plus y squared? Which associations you get when you see it? Do not hesitate. I know you with this association. Circle or distance, right? If you have x and y are offset from origin, and then x squared plus y squared will be radius, distance, right? So suppose we have nx equals 5 and ny equal 1. Here will be distance, which will be square. We also need square root, right, for the distance. 5 squared, 25 plus 1. So approximately 5, square root of 26. And if you have a state here, maybe somewhere this one, 4 and 3. What will be the distance?
Square root of 26.
Let me try. 16 plus 9. How many? 25. Right? So they are very close. So they're right now. I don't know how to tell it in a good words, in a like comprehensive words, but there are several combinations of nx and ny quantum numbers that will give approximately the same energy. If you're taking notes, try to write it in some legitimate verbalization. You may verbalize it better than I do.
Can you say that again?
So we are in the space of quantum numbers for two-dimensional worlds. We can compute energy for like this pairs of quantum numbers are represented by these little dots or circles with projections nx and ny. For each pair of nx and ny, we can find the energy, which will be associated with the distance from origin. Like if we divide energy by n naught, it will be just nx squared plus ny squared. And we notice that there are several pairs of these two quantum numbers, nx and y, which will give approximately the same energy or the same radius from the origin. So different quantum states give the same energy. How would you call it? We were discussing this word with Bill. If there are certain different states which give the same energy.
They're degenerate.
Yes. Okay. Did I tell you a story about how I learned this word? So my origin is not native of this country. When I came as a postdoc to Oregon Center of Optics, they had a very nice secretary. Probably her ancestors were from high society, so she was fine language. And I was asking to help me in preparing like abstract for a conference. Like, can you proofread my English? And she, it looks okay, but you know, there are some words that are not good in good society. So, you know, this word means some people that are going down and do not perform well. What? Degenerate. So when we speak about the quantum levels, the word degenerate doesn't have negative connotation.
So degenerate is the quantum levels of different energies.
Yeah, yeah. If quantum states, different quantum states have the same energy, we call them degenerate. Why? Why not? I just like the letter R so much because we can introduce distance in the space of quantum states. So in fact, it is energy divided by E naught. But we can call it R squared. This distance will be the square root of this stuff. Just one. The radius in the space of quantum states. Now, we need our helper, our friend, who was named by Alex Hart as a tortured student. So we need this little
tortured student or whatever, our helper, who is going forward but looks backward. So this helper is going outside from origin but looks inside. And the question is, how many quantum states are enclosed in the area behind certain energy, behind certain radius?
Pi r squared.
Divide by 4 because it is like quadrant.
Oh,
If our n, x, and y are positive, right?
yeah. Yeah.
Good. So we have the area. Basically, you have everything you need for derivation. But let me just try to do it slowly and surely.
So wait, the area of that would be the number of states that we have total.
Right.
Okay.
And then we need, but there is only one tiny problem. Right now, we express this area as function of radius. And we need to express it as function of energy, which is not a big problem, right? Our radius is E divided by E naught. We just need to plug in the value for E naught. Right? And then we will have an equation for number of states as function of energy, and we will just take derivative of it. And this will be density of states. We expect, based on your successfully completed lab and homework, that it will be straight line, constant. But we are going to prove it. Just don't want to write too much because I may have. So this is our E naught. And this is the radius in the space of quantum states. And if you are interested in all these tiny details about size of the box and constants, we can keep this long equation, although replacing it by E naught would be not wrong. So we can express 1 over E naught. We can express the energy. No, this is E naught. E naught times r squared. And then if we need to, we can swap this dependence. We can put the energy, the radius as square root of energy divided by E naught. And this constants are just to keep it universal. Now, we are computing the number of states that have energy less than some threshold. So this is area of circle in the space of quantum states, and 1/4 comes because it is a quadrant, right? And we can plug into here the expression of square root of E divided by E naught. So now we are staying in front of very complicated algebraic problem. Take square of square root, which I hope you can complete. You see, I was not kidding. If you would get just blank pages, you would be able to do it. It's not a big problem to take square of square root. So you have 1/4 pi and this square of square root, which is just in this red box, you can write E over E naught. And if we cancel a couple of factors, 2 and pi there and here, we have the number of states that do have energy less than some certain threshold will be equal to this threshold times some constants. So as far as energy grows, number of states inside this circle grows proportionally to this energy. And the reason for this that there is an effect of degeneracy. As far as we go to higher and higher energies, there are more and more states that different states having the same energy, right? So energy increases, number of states increases. What is our next step?
Take the root of it.
Okay, it's a big challenge and big check to your calculus teachers. How well are you trained in taking derivatives? So what is derivative of linear functions?
Constant multiplied with.
Yes, correct. So if you take derivative of number of states, you are getting constant. And this constant can be, well, it is known. It is proportional to the square of the box, to the mass of electron, inversely proportional to pi and Planck constant. So this is what you've got in your homework for square plate for sushi. As energy increases, density of states stays constant. Because it is associated with electron motion in x and y dimensions, in two dimensions. As soon as we got activation to the next quantum state in the third dimension, we just ramp up by a constant and then continues growing. So the consequences for big life, if you are exposed to semiconductor nanoparticles, and if you have at your disposal the instrument, well, scanning tunneling microscopy is very similar to electrochemistry, but it is more like gentle and tiny. So it's reads not only the lowest states, but the whole range of states. And it is a tool that is able to measure density of states literally. Just put sample, measure. So if you are getting measured density of states in this stepwise structure, you can, okay, there is something two-dimensional there, right? And if you are following the news, there are a lot of research and scientific discoveries for two-dimensional materials, which are examples of two-dimensional materials. Sure. Well, quantum pizza box. But which materials are true two-dimensional?
Circuit board?
Circuit board, it is more like engineered device. Film, photofilm for taking, or maybe something really nano-sized.
Yeah.
I don't know how we are about. Okay, general 6 minutes, and we are about 50% done. Do you know any Nobel Prize holder who was writing down his hamster as a co-author of a paper?
Can't say I do.
So A couple of years ago, there was a Nobel Prize in Physics for graphene, and Game and Novoselov. So once they made a joke, they wanted to prove that journalists would not check who are the authors, and he just added initial like TR Hamster as a co-author of and the paper was published. But what they were, you know what graphene is?
Yeah, isn't that they just, it's like a superconductor, and they like put tape on something and ripped it off. And
Exactly, right. You know about it. But what is like chemically?
Carbon.
Carbon.
Sheets of carbon.
Sheets of carbon. So can you draw the chemical structure?
So like a bunch of hexagons.
Yes. Yes.
It's like really good.
So
Did you have days long?
No.
Um,
Somebody else did.
In
So-
junior seminar, somebody did a
Uh-huh.
presentation on it.
So it is one two-dimensional material, which is a little exotic, but there are more, how to say, standard two-dimensional materials. Tungsten sulfide or molybdenum sulfide. So they form like MO, S, and then it goes again MO, SS, and then it repeats as a tiny sheet in all dimensions. So if you measure their density of states, you may want to expect there will be steps. Or the mentioning about circuit boards was also correct. If you're not doing the circuit board as a whole device, but just prepare thin film of silicon with intentions to carve board out of it, with the as thin as few nanometers, like 10 nanometers or whatever is today's structure. And sometimes on the CPU processors, they're like, we're proud to use 18 nanometer structures in our CPUs. So it will be as thin as like few nanometers, and you try to measure the density of states if you have these steps. Ben, did you ever seen stepwise density of states?
Not that I recall.
Because which structures do you do computationally?
Quantum dots mostly.
So it is zero-dimensional. Therefore, he doesn't have these stepwise structures. Otherwise, he would see them. Okay, done with 2 dimensions. Now our helper goes in the space of three-dimensional space. Instead of circle, it will be sphere. Right? And I know that at least one of you remembers the equation for volume of a sphere. Maybe not all of you do. So we do the same thing. We establish radius in this space of quantum states. We express amount of states inside the sphere, express it as function of energy, and take derivative, right? So number of states is 1/8 because it is octant, one of the positive numbers for third pair cube, and R will be nx squared plus ny squared plus nz squared, right? And we can do the same thing as our radius is square root of energy. And here we have Q. So for the number of states, it will be energy to the power 3/2. Now, big challenge for your calculus. If you take derivative of the independent variable in the power 3/2, what do you get?
1/2.
Yes, you're right. I'm getting the same. So density of states for three-dimensional objects will be some constants times square root of energy. So if you're, here are just details with all constants. So when you were comparing your density of states computed by summation of delta functions. And the theory curve was square root of energy. Right? And now you know where it comes from. From finding volume of sphere and taking derivative. Which slide I'm going to get? Yeah. And we already played the movie at the beginning. We did. Have a nice weekend. We are exactly in time. 11:50.
My bad.
Yeah, because we don't have all that here.
Yep, that's about
Chargers gonna win this weekend?
it. They got it. Yeah.
Yes, they do. But I
Have
don't
a
know.
good weekend.
Unless you can do two.
Either.
Oh, what one was that between Eagles?
I'm pretty sure the Eagles stopped the Giants. It was before the second half.